Howdy guys, we're here to learn about double replacement reactions. We want to take a look. First, I want to show you in our notes where we should be looking at is if we're looking at, we covered this part about solutions, suspensions, and colloids. We're going to skip this part at the moment in our notes. We'll get back to that in the next video. And we're kind of going over this part now. I will not follow the notes exactly, but you can use this as a reference if you'd like. So just want to give you a reference point. Just kind of follow along, okay? Now this is also attached in our in your assignment. I'm going to go through this step by step in a second. So let's go ahead and begin. We want to talk about double replacement reactions. So just a few bit of vocabulary words. A double replacement reaction, if you recall, was one of the 5 reactions that we had to know before. We had synthesis, decomposition, single replacement, double replacement, and combustion. Well, the double replacement is where two dance partners are switching, 2 metals are switching to create 2 new dance partners, right? So this is also known as a precipitation reaction, okay, because it creates a precipitate. Hopefully you watched Lee Merrick's video before this. If not, you should stop and go watch that real quick because he does a good example of what's going on a molecular level, but also on a macroscopic scale. So now there are 2 important terms you need to know, and that is soluble is a substance that is able to dissolve in a particular solvent. So if it's soluble, it means it can dissolve. And if it is insoluble, it cannot dissolve. Okay, so I'll use those a lot. Now the precipitate, hopefully you got to see, was a solid that forms when 2 aqueous solutions are mixed. Okay, so it's the solid that forms when 2 aqueous solutions are mixed if, and that precipitate is always the insoluble form, okay? So in these double replacement reactions, let me move my head and make me smaller. So in order for a double replacement reaction to happen, it must produce a precipitate. So right here we have our 2 aqueous solutions right here that are added. Often they're going to be colorless. Remember, clear is not the right word. We want to use the word colorless. And they will produce a colored solid. Okay, sometimes it's white, sometimes it's blue, sometimes it is yellow, or all sorts of different ones. I can tell this one is chromate because it is yellow. So that's a telltale sign of chromate. So that would be lead chromate right here. So we will use this solubility rules table right here. Now what we're mostly focusing on is right here, the stuff in the middle. We're going to look at the stuff on top and the stuff on bottom. Now the polyatomic ions you should be familiar with. Make sure you understand those because those will be necessary here. This is it blown up a little bit, and this is it blown up down here. So I'll go back. Now the top part is going to show us which ones are soluble, and unless they are in some kind of exception right here. So for example, the bromate ion, the bromide ion is going to be soluble always unless it is with silver, lead, or mercury, okay? Unless it's paired there. And this will make sense as I do some more examples. But the nitrate ion is always going to be soluble, okay? No matter what, no exceptions. So down here we have some insoluble ones where we have the carbonate ion is almost always insoluble unless it's paired with something that an ammonia or an alkali metal. So those alkali metals you can see are the group 1 metals, okay? Now, so if we use this solubility chart, we can use it to determine right here. So why don't I just start going through some examples and see if we can use that solubility chart. So I'm going to go through these 12 pretty fast, okay? Now, Man, my head just keeps getting moved around. All right, so here we have soluble, insoluble, and then we have our soluble, insoluble, and soluble. Now, if we have number one, we have iron chloride. Well, let's split it up into its ions. Okay, so we have iron and chlorine. Well, let's see if we can find either iron or chlorine on the list. Okay, here's chlorine. Okay, so chlorine is always going to be soluble unless it is with silver, lead, or mercury. Well, it's not with silver, lead, or mercury, it's with iron. Okay, so we're going to call that aqueous. We're going to call it soluble, okay? Because if it's soluble, it dissolves in water, it's aqueous. Now let's look at KOH. Now there's no potassium on here, but there is a OH. So down here we have OH. It is insoluble unless it is with ammonia or an alkali metal. So since it's with an alkali metal, potassium, it is actually still going to be soluble. Here we have KCl. KCl is here. It is going to be soluble. And then iron hydroxide. Look at our hydroxide again. And let's see. It is going to be insoluble unless iron shows up on this list. And iron's not here, so we're actually going to call that a solid. Okay. So we have ammonia sulfate, number 5. Let's look at our sulfates. There is no, sulfates are soluble unless it is with, and its exceptions is not, and ammonia is not part of one of the exceptions, so we will call it aqueous. Sulfates are soluble. Now silver nitrate. Well, we can see that all nitrates are soluble, so we'll make that aqueous. Let's see, lead sulfate. Here, sulfates are soluble, but we have lead here present. So since lead is present, it is now going to be an exception. So it is now going to be insoluble. It's going to be a solid. Okay. Now we have manganese hydroxide. And hydroxide, they're not very soluble unless they're with a group 1. So we have, this one's going to be solid as well. Okay. Now sodium bromide, we have bromine, and that's going to be soluble. Silver chloride is a solid. Now chlorine is a soluble compound, but it's in the presence of silver. So since silver is there, it is now going to be a solid. So sodium nitrate is going to be aqueous. And then barium sulfate. Let's see, that sulfate right here. The sulfate is soluble, but it has barium present. So therefore, barium sulfate must be a solid. Okay. So just some 3 general rules of thumb right here. I like to keep these in here, and it'll answer about 90% of your questions. That all nitrates are soluble. All group 1 salts are soluble. So that basically means anything that has anything group 1. So lithium, sodium, potassium, rubidium, or cesium. And then all ammoniums are soluble. Okay, so if you keep those 3 in your head, it answers just about any one of those. Okay, so let's see if we can predict products now. So this is going to be the fun part. This is when we are going to try to look at KCl and silver nitrate. So this is similar to what Lee Merrick did in his video, where he combined 2 solutions together, 2 aqueous solutions. And he said that remember that whenever it's aqueous, that really means that we have K plus and Cl minus swimming around. Like they're swimming around in a homogeneous solution, right? In even mixtures. So as these are swimming around and as these are swimming around, some of these and some of these will come in contact with each other. When they do, we'll see if they make a precipitate or not. So let's see. So we have potassium, and then we have chlorine. Those are swimming around. We have silver, and we have nitrate that are all swimming around. Now what will happen is potassium will come in contact with the nitrate, okay? And then the silver will come in contact with the chlorine, all right? So let's see what kind of products we would make out of that. Basically what I'm doing is I'm taking the outside ones and pairing them together, and taking the inside ones, pairing them together. And so I'll end up with K+, and then I'll end up with nitrates. And these polyatomic lists that you have on your reference sheets are going to be helpful. And that K plus and nitrates, it's the +1 and the -1 will cancel out to make potassium nitrate. And then we have Ag and we have Cl. Ag is a +1 charge and Cl is a -1 charge. And so those plus and minuses also cancel out. So now we need to determine if they're soluble or not. We need to determine if it's aqueous or a solid. So we know that all nitrates are soluble, so KNO3 is always aqueous. Now silver chloride, well, we have to determine from our list before that since all chlorines are soluble, but if it's paired with the silver, then it is going to be insoluble, which means it's going to be the precipitate, silver chloride. Let's try that one more time. That means that a precipitate or reaction will occur. So here, let's take our first term in our, if we have lead nitrate and hydrochloric acid, lead nitrate will split apart, and then hydrogen and chlorine will split apart. The outside terms will pair together, and the inside terms will pair together. So let's try to remember what charge was lead. Well, lead, Pb, since nitrate was a -1 charge, and it always is a -1, you can tell that from your polyatomic list. And we needed 2 nitrates, and so we needed 2 -1 charges to cancel out our +2 charge right here. So that means that lead was a 2+ charge. And then we have chlorine right here, which is a -1 charge. Okay, so a 2+ and a -1 right here. If we crisscross those charges, our product will be PbCl2. And we have H+ and we have NO3-, and those will cancel out to make HNO3. Now, first off, we know that all nitrates are soluble, so for sure this one's going to be aqueous. Okay, we also know that hydrogens are soluble, so that's aqueous as well. So now let's see if this one is soluble. Let's look at our chlorine again on our list, on our solubility rules. And if we look at chlorine, it is soluble unless it is with lead. Okay, so it's going to be a solid, and that's going to be aqueous. So the precipitate will occur, and the precipitate will be PbCl2. Now, don't forget to balance this one. Whenever you make these products, there's always that key that sometimes you'll have to balance, because we only had one chlorine over here at first, but we have 2 chlorines over here. We needed that, so that's going to be helpful. We also need that too. We want to predict the products of each reaction, include the proper subscripts, include the state symbols for all species, including reactants, and balance the reaction. The first part is easy because all of these are going to be aqueous, all reactants. First, let's try to take our first term and our last term and try to pair them together. So let's take NaCl. And let's take our inside terms, H and CO3. H and CO3 doesn't exist because H is a +1 charge and CO3 is the 2 minus charge, so we have to crisscross them, and so that ends up being H2CO3. This one's okay, this is a +1, this is a -1. Okay, so that's what I mean by putting the proper subscripts. What I like to do is I like to write out the letters first, or put as much as I can, and then I like to fix up the products after that. So now I need to decide if they're soluble or not. Well, I know that all group 1 salts are soluble, and then this is soluble. So this is actually going to have no visible reaction. Let's do this one. Well, let's have Na and Cl, first term and last term, and let's have our inside terms, nickel and carbonate. Just like usual, write out your products and then double check to make sure the charges are okay. We have +1 and -1, so that cancels out. I know that they're +1 or -1 because I know on my periodic table, sodium is a +1 charge, it's in the first group, and then chlorine is a -1 charge, it's in the 17th group. All of these are -1. So nickel is a +2 charge over here. So the rule says that it has to be the same charge on either way. The charges don't change. And then carbonate is a -2 charge. +2 and -2 cancel out, so I don't need any subscripts. So this one is aqueous here. Now let's see if this one is soluble or not. So we have nickel or carbonate. We're going to find either nickel or carbonate here. And so I find carbonate. Carbonates are insoluble unless they're with this stuff, but nickel is not one of them. Nickel is not an exception, so this carbonate will be insoluble. Okay. Just a side note, the state symbols can be written here. They can be written off to the immediate right, or they can be written in the bottom right corner. It just depends on where your professor likes to do it. Let's keep moving, and let's move on to something like if we have the first one here, the last one, we end up making NaCl again, which experience tells us is going to be aqueous. And then if we have potassium and we have nitrate here, well, I know that all nitrates are soluble, so I can just mark that off as aqueous. Again, that will have no visible reaction, because all of the products will swim around in solution just like all of the reactants are swimming around in solution, exactly the same way. Now check it out. Let's try the next one. Let's do copper and chlorine. So Cu and then Cl, and let's do barium and sulfate. Okay, just like I said, I'll write them out first, and then let's see if we can make our subscripts make sense. Let's see. So we know that copper is a transition metal. We're not sure about its charge, but we are sure about sulfate's charge. Sulfate was a -2 charge, so that we can make sure that must mean that this one was a +2 charge, +2, and so this one has to be a +2. The charges can't change, and so chlorine is a -1 charge. We know that one for sure. So barium had to be a +2 charge. 2 -1 charges balance out a +2 charge. So barium had to be a +2 over here. The sulfate group was a -2 charge, and the chlorine was a -1 charge. So that is telling me that I need 2 chlorines right here. All right. Very cool. So since I need 2 chlorines, that means, okay. So let's see if they're soluble or not. Well, copper and chlorine, let's look. We've tried to find copper or chlorine on the list. We have chlorine here. So chlorine is soluble unless it's with these guys, but copper is not on the list. So that must mean that chlorine is soluble. So this one is soluble. And the barium sulfate, let's check out sulfates. This sulfate is soluble, but unless it's with barium right here. So if it's paired with barium, it must be a insoluble compound. Okay. So this one must be insoluble. This must be my precipitate right here. Very nice. The last thing, that is a balanced equation, so we're all good. So let's do lead. We have lead nitrate, and then we have potassium iodide. Here's PB and I. So let's do PB, PB and I. And then let's do K and NO3. All right, so let's fix our products now. Let's see, we know that nitrate from our list right here, nitrate was a -1 charge. So we're gonna pop that one over and we're gonna say that this one is a -1 charge. We needed 2 -1 charges to cancel out our positive charge. So that must mean that this is a +2 charge. So lead was a 2+. This one was a 2+. And then iodine right here. Iodine's in the 17th group, so it's a -1 charge. This one's a +1 charge. And so we just transfer our charges over here. Iodine is still -1. And potassium is a +1. Nitrate's a -1. So these +1 and -1 cancel out. So this one's fine. But the iodine, we need 2 iodines right here. 2 -1 charges to cancel out a +2 charge. So now let's see if they're soluble. Well, this one is always soluble because nitrates are always soluble. And we also look at lead iodide. So iodine is soluble, but if it's with lead, it's insoluble. So that must be a solid. That's our precipitate here. Okay. Much the same happens over here. Let's try this one. This one will end up being lead chloride plus potassium nitrate. And this one will also be soluble, a precipitate, because our chlorine is a -1 charge and we have our lead right here. And let me see if I can get one a little more exciting. Let's get number 15, because this one's a good one. This is actually an acid, and this is a base. We'll see this in our acid-base unit. But acid-base reactions work the same way, where we have a hydrogen and we have a hydroxide right here. This hydrogen and the presence of a hydrogen makes it an acid. The presence of a hydroxide makes it a base. So let's go ahead and write it out like we would. Let's take our first term and our last term, which is going to be HOH. And then let's take the inside terms. Let's make sure we name the metal first. So NaCl. Okay. Now, NaCl, this is a group 1 salt, so this is going to be aqueous. And then we have HOH. Well, that's actually H2O, right? And H2O is not aqueous, it's a liquid. All right. So, yes, this reaction will happen. This is a reaction, okay? There will not be a visible reaction, but it is a reaction because we are changing phase right here. This is going to be aqueous, and this is aqueous right here. Aqueous and aqueous, this is a liquid. So it's this change of phase that makes it a reaction, okay? If a side note, an acid-base reaction will always produce a salt and water. Let's try one more, just to boil your brains a little bit because this one's fun. Or actually 2 more. If we have H and S, we get H and S. And then we have Na and Cl. Prior experience tells us that this one is aqueous. And let's make sure our charges are okay. We have hydrogen's a +1, sodium's a sulfur's a -2 charge because sulfur's right here. Sulfur's in the 16th group. So all of these are -2. So that one has to be a -2. This one has to be a +1. So that must make this H2S. Okay, we needed 2 +1 charges to cancel out the -2. Now, H2S is actually a gas. All right. That's something a little extra that you need to know. That's a little icing on the cake, if you will. All right. So this is actually very dangerous. We do not do this one in the lab because H2S gas is lethal. All right. And then we have NH4 and OH. Let's make this NH4OH. And let's make Na and Cl. Fun fact, NH4OH will spontaneously decompose, and you wouldn't need to know this for your test. It's just a fun fact. It will decompose into ammonia, NH3, and water. Okay, one of these hydrogens will pull off and join this, and then we'll still have that salt left. Okay, now ammonia is a gas, water is a liquid, and then sodium chloride is aqueous.